Welcome to This Explainer. Today, we're diving right into Elon Musk's Neuralink product demonstration. We're looking at a piece of technology that honestly sounds like it was ripped straight out of a sci-fi novel, but as we're going to see, it is rapidly becoming a reality. We're going to map out exactly what this device is, how it's actually installed, and explore its incredibly ambitious goal to solve critical brain and spine problems with a completely seamless implant.
To kick things off, it really helps to ground all this high-level tech with a brilliantly simple analogy straight from the presentation. When we hear brain-machine interface, we usually picture these incredibly intimidating arrays of wires, right? Big external computers, lots of hardware. But this quote completely demystifies what we're actually dealing with here. Musk described it as being kind of like a Fitbit in your skull with tiny wires. It takes this seemingly impossible futuristic concept and frames it into something we already know, understand, and probably wear every single day.
So here's our roadmap for today's explainer. 1. A Fitbit in your skull. 2. The automated surgical robot. 3. The three little pigs. 4. Healing the human body. And 5. Replaying memories and beyond.
Section 1. A Fitbit in your skull.
The hardware itself has undergone a pretty dramatic physical simplification. Just a year prior to this demo, the Neuralink prototype was highly complex. It had multiple parts, including this bulky piece that literally had to sit behind your ear. Basically, it meant you wouldn't look quite normal walking down the street. But this new version 0.9? It's been totally consolidated into a single device roughly the size of a large coin. It's designed to be completely invisible once implanted, sitting totally flush with your skull.
Now, the crucial thing to understand here is that this tiny version 0.9 prototype isn't just small, it is remarkably powerful. It packs in 1,024 separate channels, or microscopic electrodes. To put that number into perspective, that density is about 100 times better than the next best consumer brain interface device available today. And that density is a massive deal, because more channels means significantly higher fidelity data when we start reading and writing those neurological signals.
So how does this actually integrate into your daily life? Well, let's look at the dimensions. The human skull is about 10 millimeters thick. The Neuralink itself is 8 millimeters thick and 23 millimeters wide. A tiny piece of the skull is removed, the device drops in, and it sits perfectly flush. Under your hair, no one would ever know it's there. And just like that Fitbit analogy, it has an all-day battery that charges inductively. You literally just charge it wirelessly while you sleep, exactly like you do with your smartphone.
Section 2. The automated surgical robot. Getting 1,000 microscopic wires safely into a human brain requires micron-level precision. These tiny threads are actually thinner than a human hair, which is way too fine for even the best human surgeon to place accurately without causing damage. So they use an advanced automated robot. This robot images the brain in real time, actively mapping it out to dodge veins and arteries. It then inserts the electrodes with such crazy precision that there's no bleeding and no noticeable neural damage.
The ultimate goal of all this robotics is sheer accessibility. They want to make this highly complex brain surgery as automated, routine, and seamless as getting LASIK eye surgery. Think about that. You could potentially walk into a clinic in the morning, have the robot do its thing in under an hour, without even needing general anesthesia, and walk out that very same afternoon.
Section 3. The three little pigs.
Okay, so to prove this concept actually works in living subjects, they brought out 3 live pigs. First up was Joyce. Joyce was a completely healthy pig with no implant, serving as our control group. Next was Dorothy. Now, Dorothy is super important because she used to have an implant, but it was removed. She proves the whole procedure is reversible. You can get it taken out or upgraded without any lasting health issues. And finally, there was Gertrude. Gertrude had a fully active Neuralink running in her head for 2 solid months. The absolute highlight of the whole demonstration centered on Gertrude. During the presentation, the audience heard this rapid series of beeps, and those weren't simulated sounds. They were actual, real-time neural spikes, electrical brain signals, firing directly from the 1,024 electrodes in Gertrude's head. The implant was tracking the neurons connected to her snout, so every single time she snuffled around on the ground or touched some food, the device wirelessly beamed out that distinct activity.
But hey, reading basic sensory spikes is just the tip of the iceberg. They also showed that by taking these wireless neural readings from a pig walking on a treadmill, their computers could actively predict the physical position of all the pig's limbs. And when they compared their predicted positions against the actual physical positions of the joints, they aligned almost perfectly. It proves that just by reading brainwaves, the system can interpret physical movement and intent in real time.
Of course, reading data is only half the puzzle, right? Writing data back into the brain safely is the other half. To prove they could do this, researchers used this fascinating technique called two-photon microscopy. It basically let them look directly into the brain tissue in real time. They could literally see red flashing elements, which were the electrodes firing electrical currents, and immediately see green neuron bodies responding to that specific current. This proved that precise, targeted stimulation is possible without frying or harming the brain.
Section 4. Healing the human body.
So why does all this matter for us right now? Well, the immediate focus for this technology is heavily medical. Neuralink actually received a breakthrough device designation from the FDA. They're working extremely closely with regulators, and their very first clinical trials are directly aimed at treating patients with severe cervical spinal cord injuries, specifically folks dealing with paraplegia and tetraplegia.
The long-term medical application here beautifully leverages everything we've talked about so far. Let's just take a second to really digest this. If a patient has a broken spine, their brain can still generate the intent to move, but that signal physically can't reach the limbs. By using a Neuralink in the brain to read the movement intention and a second implant placed below the spinal injury, they can create what's called a neural shunt. It essentially acts as a wireless bridge, transmitting the brain's commands right over the damaged area. It bypasses the broken spine entirely. The long-term goal? Confidently restoring full-body motion to paralyzed individuals. Absolutely incredible.
Section 5. Replaying memories and beyond.
Now, once you establish a high-bandwidth, whole-brain interface, the possibilities step firmly out of the hospital and straight into science fiction. During the presentation's Q&A, this massive question from Twitter was raised. Someone asked, simply but profoundly, will you be able to save and replay memories in the future?
Elon Musk's answer to that was a resounding yes. Acknowledging how absolutely wild it sounds, he even joked that it was sounding increasingly like a dystopian episode of Black Mirror. But the underlying logic really does hold together. If everything in a memory is essentially encoded electrical signals, a whole brain interface could eventually allow you to interpret and capture those signals. The claim is that you could store your memories as a digital backup, restore them, or ultimately, and this is where it gets crazy, download your consciousness into a new human body or even a robot body.
Now you're probably thinking, okay, this kind of tech will only ever be for billionaires. But the stated goal is actually mass accessibility, because the physical implant relies so heavily on electronics that are already manufactured in the tens of millions for our smartphones and wearables. The cost of the actual parts is incredibly low. Over time, by combining those cheap parts with the automated robotic surgery, the goal is to drop the total price down to just a few $1,000s, very similar to what you'd pay for modern laser eye surgery today.
As we wrap up this explainer, I want to leave you with one final profound thought. We are looking at claims of a future that is guaranteed to be weird, fascinating, and utterly transformative. When the day comes that our physical ailments can be bypassed with a wireless shunt, and our very memories can be backed up to a hard drive and downloaded into a robot body, what will it ultimately mean to be human? Thank you so much for exploring this wild topic with me today. Keep wondering and keep learning.